All right. Good afternoon, or good evening, I should probably say. Thank you very much for coming to my talk at this late time of the day, especially given that there's so much beautiful weather outside. I would probably rather go to the beer garden than listen to this talk, but I appreciate you coming here. Also, yeah, I think in an earlier version of this talk, I gave at a Vox Days Luxembourg last year, and this was my first Vox DevVox ever kind of speaking experience. And I think I had less than 10 people in my talk. I was pretty disappointed. So I was hoping if it gets accepted at DevVox, I might get more than 10. And so thanks for making this dream come true today. And now, before I talk more rubbish, I probably go into some more content. All right, so this is going to be, as a long title, this is basically going to be about Java and containers. And I'm going to talk about different possibilities, how to build your Java application and build a container out of that, and show you various options and probably pros and cons of these. Maybe a few words about myself. My name is Matthias. I work for a software engineering company called Novatech in Germany. I can be found on social media, mostly on LinkedIn and Twitter, or like X now, but I still have the bird icon there. Besides that job, I also do, I teach at universities. I teach in the area of distributed systems and modern software architecture. So I also always try to integrate those new cloud-native technologies into traditional fields of software engineering. All right, so yeah, this is where we're going to go. I guess most of you have built a Java application in a container before and have heard about things like a Dockerfile. So this is certainly something we're going to look into today, but we're also going to look at various other options and various ways to do that. I hope there is something in there that you didn't know yet, and I can show you something new. But yeah, let's go. So I've also given this talk as a kind of hands-on lab, and there is a GitHub repo available. You can check it out. So everything in there is, of course, open source. And you basically just need a container daemon and a few tools to walk through it. So within those 30 minutes, I probably not have enough time to cover each and every aspect of that. But if you think this is something you want to repeat at home or so, this is basically where you can look into. All right, in a longer version, I would also go more into details of like, yeah, how are containers internally built and how did it come to containers and so on. I'm going to cut this short. But nevertheless, I would want to make sure that we're all talking about the same things here. So with this little sketch, I wanted just to show what my understanding of a container is. So you have like an isolation layer for your process or application that contains all the libraries and binaries that you need to run your so-called containerized process. And the technologies that make that possible are somewhere in the Linux world called namespaces, change root, and C groups to say, okay, this is like the visibility level of that container, and this is the resource that can use. And basically, these are the things that give the container the idea it lives it's kind of in its own world. So you can technically do this if you're very familiar with namespaces, change root, and C groups. But I think it became more popular when the people, especially at Docker, kind of said, okay, they're going to write a lovely API around that to make things easy and handle all that low-level Linux stuff under the hood. And that's kind of when containers became really popular to the mass market. Now, a container image is basically the blueprint or the template, or however you want to call it, that you will instantiate to create containers out of it. So seeing it from a Java world, you could potentially say this is the class, and then the container is like the instantiated object. And the container daemon is basically the you can say your virtual machine, or like, well, like your runtime that runs your containers. I guess most of you have heard about that before, but I just wanted to go sure. Now, interesting. I mean, if you want to compare how to build containers or like container images, it's important to understand how they're internally built. And they're built using kind of a layered mechanism. So a container image is not just like one big blob. It's built on different layers. They're individual kind of zipped components. That makes containers more efficient. So to say, if I have multiple different containerized applications, but they have a similar stack kind of underneath, the container daemon needs to load those layers only once. And that's kind of a point where you can make things more efficient. In the very beginning, this is also how container got built. So you would basically run a container, then add a new layer on top, then commit into a new image, then run it again, and commit again, and so on. So this was probably a very painful process. And that's when Docker decided, I think this was in May 2013, and it came out in March 2013. So that was the first entry when that term Dockerfile appeared. And this is basically has been in use ever since. So yeah, even today, if you go, for example, on the Docker Hub and look up the Tamarind image, this is like the documentation that you get, how to build a Java application that you previously built. So these are 4 lines of a Docker file, which will then turn into an image by using this command below, and after that you can run it. So technically speaking, it works like a kind of a shell script, goes from top to bottom. It loads a kind of such a base container. This is like the lowest level. And then for each line in the Docker file, a new kind of container image layer will be generated. Now, as this is called, and you will see to do that for your Java application, you of course have many options. And with those options, this is also where kind of the problems come in. Because normally the developers would probably not want to worry so much about the underlying layers in their container. They would just want to code their application and get it to run somehow. But this underlying layers in the container image is basically also something they turn responsible for, because they built the container files, and that means everything they pull into such an image can be kind of made like they can be held responsible for. So this is an example where you have like a base Linux image, then you install a JDK, copy your code, and then basically assign that command, which will basically tell you whether you do a Docker run, this command will be executed, and it will hope to find this jar file. The jar file will hope to find this JDK, and then it's going to run. Some people have already come there and said, okay, we probably don't want to build it all from scratch over and over again. We also have some base image that have an OS stack and a Java runtime in there, so that makes it shorter. Also, but that causes the problem again, which is the right runtime. This problem is what you probably have in Java even without containers. But still, what you can't see from here is what is beneath that runtime. So which kind of Linux distribution is there? What kind of libraries and binaries are in that base layer? And that can sometimes just go into a direction when there's a new exploit or vulnerability coming up, and you're in the situation and say, okay, is that in my container or not? Anyways, this is called tools in action, so I'm going to show you some tools in action. What is that? Bigger font? Okay, thanks for that hint. I thought the screen is big enough, but I can certainly make this bigger. So is it good to read now? Okay, thanks for that hint. So to start with a very simple one that I just shown. So we have the 3 lines of code here. You would say docker build, specify the Docker file, and which is called simple Tamarind, and then I specify the tag. So I'm going to say Java simple Tamarind, and then this process basically takes place. The container gets built. You basically see the individual steps. And this happens very quick. So if I go on Docker images now, I see this new container on the top, hopefully. So this has, so it's too big for me now. I have to make it a little smaller. So we can't see this one in here because I have built it before and the code hasn't changed as a build from before. It's basically the one that I already built today in the morning. So I can still go and say Docker history and say the container name was, got too many images, probably know that problem. So with this history command, it will basically show you all the various layers that have been used to build this image. And this missing part basically shows you this is what has been pulled in from that base container, and you don't really know actually what's going on in there. You only know that those top layers is where when we put our jar file in and then we specify that command. So that's potentially dangerous area because we don't really know what's kind of happening in there. All right, and I could of course build other ones. The process is always the same. So we're going to go a bit further here. Now, one thing which is also a bit of a problem here, those base images tend to get out of date like any kind of software. And often this is kind of specified on the public like registry where you can pull them from. But you're not going to get notified about that when you build that container. And this has happened to me before, that I actually gave this talk and was using an image that was already deprecated. So this can happen, and this is not so easy to notice. And again, this is something the developers or the builder of the container images should be aware about. Now, the evolution of that didn't stop at that point. In 2017, Docker released that thing called Multistage. Multistage Dockerfiles, which basically is the same concept. You still have this kind of process of the file from top to bottom, but you build different containers. So in this here, you can see that from clause, and say you're using this as a build container. So you copy all your code in, and then you build your application inside the scope of a container. The advantage of that is that everyone who runs that Docker file will have exactly the same build, and you prevent it from people building on their own machine and checking in Javas like that or something like it. And that, of course, increases consistency, but it also increases the runtime of the application. So if I show that real quick here, so I'm going to say, I'm using this one, the multi-stage builder. And when I execute it, you will probably see that now okay, this one didn't do anything because I built it before. So let me do a quick change in the source code that there is actually, so I'm going to just say this method should now be called ABCDE. Not a big code change, but big enough to basically pick up the build again. And now it's basically starting to do the Maven build stuff. And as it is in a container, it doesn't know it has been running somewhere before. So it has to build the cache and pull all the libraries. So that is definitely something which makes it very well consistent, but it also takes a bit of a long time. I will leave that running and move forward, because the evolution moved forward here as well. There was the so-called Docker build kit step. And this kind of transformed the Docker build mechanism quite a bit. So these were the things that it was advertised for, like faster builds, smaller images, better flow logic, and so on. But one of the things that I found particularly interesting was the improved caching. So you could also do now run like different stages in parallel. It basically turned it even into some kind of programming language, which was probably not the intention and caused complexity on another end. But this mount thing was particularly interesting because previously it was not possible in a Docker file to say, okay, I want to get out of the container and mount something from the file system. This is possible in containers itself, but not in the build step. So now this one has finished in the meantime. So we're seeing here this was about 71 seconds. And now I'm going to change my code again and say this time I'm going to use that, that caching mechanism. And it's technically, it's almost the same file, but you can now see the build was a lot faster because it used the Maven cache outside of the container, and so it speeds up the build time significantly. Of course, this isn't only as healthy as your cache is. If you want entire consistency, you probably have to go that way and run it from scratch all the time. But for quick development steps, this is definitely a big help. All right. So to sum things up, what basically makes a container good or better than other containers? So it's of course the speed once on the build time, once on the startup time, the size of the container, they shouldn't be so big, the structure of the layers, the degree of standardization, security, hopefully, and in the Java world also an optimal JVM configuration for your Java application. Now, in the reality, looks still like this. So this is basically the examples that we get, and there's not so much optimized structure, size, security, and so on in that Dockerfile. And I guess this is still the way that 80 or 90% of the people would use. So I've already shown you a few things that how you can improve, but there is more. A few considerations here maybe about the size and the structure. Because I've seen people very often to try to get their images as small as possible by eliminating some things on the base operating system layer and so on. However, how the container works is that the daemon is able to cache those layers, and it will cache those layers. So basically, the bottom layer is most likely not to be exchanged so often. I mean, if you exchange your base layer in a container every week, then something might be horribly wrong. What will change, however, very often is the application layer on top. So that means if you focus on that parts that only change, then you can make your things more efficient. And now if we look into like a jar file, we have a similar structure. We have like class files, we have resource files, and we have dependency jars. And again, mostly it should be the class file that change, and not so often the dependencies, especially not like with every build. So if you want to optimize, it's much more efficient to make the structure in like more granular on that level, rather than squeeze a few megabytes on the OS layer, which is basically being cached anyway. I mean, that's only going to take long for the first time it's being loaded. So one thing to do here is this extracting the jar file and splitting it into different directories. So that basically means each of those copy steps will in the end result in an own layer. And if only your class files change, then basically only this layer will get updated, while all of the others are still getting cached. So I can show this real quick. If I, like with the options that I built the containers now, so, sorry, that was wrong. And I do a Docker history, for example, on this one. No, sorry. I can still see that a big chunk like this 21.4 megabytes always comes in as one step. And this is only a Hello World application. They will probably get bigger and more complex in a real-world environment. But even if only a bit changes, it always has to copy in that entire layer. So if I use that layered approach, like I can see here, where I split all those things out, and I built that one once, and look into this, 239. I can then see that I have this split out. So the dependencies of my 22 megabytes, 20.13 are in here. And the code is only a few kilobytes. So if I split it that way, then my builds can be more efficient, especially if my services are a little bigger. I mean, it's only a minor improvement, but it can certainly help. Now, talking about those Java arguments, my colleague Carlos has given a real good talk on that in Devox UK about the various flags and arguments that you can use there. And I don't have time for this today, but if you're more interested in that, so we see an example here, like for parallel garbage collection and max RAM percentage and so on. He has done a pretty elaborate thing on this, so check it out if you want to. And you can see in the end, if you want to include all of that, your Docker file is suddenly not so small anymore. So we have the standardized build, we have the extraction into layers, we have the JVM arguments. So if you want to do it properly, it might become more complex. Another thing I just found out, looking at the blog from SNCC, Brian Vermeer has shown a way to build a container using jlink. I can show that real quick as well. This is basically the code which is here. It's also a multistage Dockerfile, which extracts the jar like analyzes the dependencies and using jlink to only build an image with the necessary dependencies. I'm not going to rebuild it now because I'm running out of time, but as you can see here, this one with 176 megabytes is quite a bit smaller than the others. So he's actually giving a talk on that, I think, on Thursday. So if you want to have more info on that, please check it out. Now, I've spent 20 minutes on Docker, which is probably more than I should have, but I still want to show maybe two other things. So in this area of container builds, there have been various ideas and things around. So one of the things that became very popular even before containers was the concept of buildpacks. This was mainly driven by Heroku and Cloud Foundry. And then there have been other things like Maven plugins to build containers or other toolings. So two that I want to show here real quick. One is called JIB. This is from Google, and it's only for Java or JVM-based applications. It basically works as a Maven or Gradle plugin. You execute it, and you're going to get your container image. The interesting thing that you see here is the thing actually that you don't see, because you don't need a Docker daemon to build that. So it will basically assemble the binaries of the image without going through a Docker daemon to build it layer by layer. This can be very helpful if you have limitations on your CI/CD pipeline or so, where you, for whatever reason, cannot use a full-blown container daemon or something like that. It still can, I mean, the exports of this, you can push it to like a registry, you can push it to your local Docker daemon if you happen to have one. So this, of course, works, but you don't need it. And you can also export it to a tar file. Now, I can show this real quick, how this works. So I'm using the first version to build against my my Docker daemon. So this will basically put a container image in my local registry. And as you can see on the first thing, it is pretty fast. And so this one took 10 seconds. And the image is down here. And if we have a look into this image, why does it not copy? 0D4. So I'm only using 3 digits here, but that Docker will automatically resolve that. Now you can also see this one automatically does that breakdown into dependency, resources, and class files. So you don't really need to specify anything. It's just one call, and you get your image, and it's pretty well structured. The other thing is you can also, as I said, push it to a registry. So I'm connected to my private registry, my public registry on Docker Hub. So this took like 8 seconds for building and pushing it. So this is pretty efficient. Now, finally, I want to talk a bit about buildpacks. So buildpacks, as I said, were an idea that even before the name of a container existed. So it was an idea from like the platform as a service world to say, okay, I want to push my code somewhere, and some higher level abstraction will take care of it, detect what kind of type it is, how to build it, and get it into a runnable format. So it was kind of a life cycle that things went through. As I said, this became popular with Heroku. Cloud Foundry adopted it, brought it to the open source world. And then somewhere here in between, this kind of Docker, Kubernetes, hype, whatever movement came in and kind of pushed this technology a bit on the outside. But anyway, the idea to build such a container in a standardized way still persisted. So this is the time when Cloud-Native Buildpacks became an own project to build those container images. And there are various implementations of this. Paketo is one, Google has one, Heroku has one. And they work all in a similar way. So there's a CLI called pack that you can use. This will download a so-called builder image that contains all the various build packs. And then it will analyze the code, use the right build packs, and in the end, create an application image. So this one is also, of course, then not limited to Java only. This will basically be able to build all kinds of images where build packs are present. So I can also show that real quick. So if I do pack, these are the options that I have. So I can say pack suggest builders, and then it will tell me what I have. So I have Google, I have Heroku, I have Paketo, and also I can build own build packs, but I'm not sure if I would really do that. And then I can just say pack, okay, build my application, and I don't specify anything. So it will find my POM XML in that directory, and then it will figure out, okay, this is most likely a Java application, pull all the things in, and drop my container out of it. So it will first check, does it have that big image where all the build packs are contained? And then it says, okay, so here it analyzes the Java version. This is all the flags that it's going to be set. I mean, you can, of course, override them, which is, of course, important if you want your own custom kind of JVM things to it. And also compared to other build mechanisms, this has a pretty nice bill of materials. So you really get a proper output and see what it has been done. You can analyze where things go wrong, went right or wrong. And so it's going to go through. The first time it is running, it always takes a little longer. But in the end, once you repeat it, it's about the same time as the others. So if I go on Docker images, one thing you will probably notice, both for that JIB component and also those build pack components, is that your images are suddenly very old. So this container technology did most likely not exist 53 years ago, or not 43 years ago. The reason why that is pretty simple. If you do a standard Docker build, then the timestamp of your build will basically walk into your container image ID. So that means you could potentially do two identical builds at two different points in time, but you get different IDs, which might make things confusing. That's why both Paketo and Buildpacks and JIB have made this standard to say, okay, all of the builds have been set to a certain defined point back in time, and that means it's much easier to identify consistent builds versus different ones. This is something you can certainly switch off if you don't need it. Then this would go away. But this is probably something that people would find confusing when they use it for the first time. All right. So yeah, what's the other advantage of this? So I told you before that most likely things change on the top of your image. Now I'm going to tell you, okay, what happens if you need to change the bottom of the image? And this can actually happen in a case, which I said before, when suddenly a Heartbleed, Log4j, whatever vulnerability comes up. Probably the first thing that comes to your mind is like, am I affected? Do I have something in my code which might cause a problem later on? And this becomes much more intense if you don't have just one stack. If you have different kind of applications, different kind of frameworks and languages, most likely your underlying runtime changes. I made this experiment with my students as well. I let them build a front end and a back end over a common REST API. But the thing was to use different kind of programming languages. In the end, we had a total mess of different base images, and if then such a thing comes up to say I have vulnerability here, it would be very difficult to figure out where am I affected and where am I not. So this is the concept of build packs, to say we're always going to use the same base layer. And if you use that consistently, of course you will always know if something went wrong, then you can easily exchange just all of the base layers. And if you're not affected, you can just leave them as they are. So that is basically what that rebasing means, that you keep your top layer with the applications and dependencies, but you exchange the one that would have a potential vulnerability in there. All right, so yeah, of course, this goes also for the Java world. If we have a look into the image that I had just built, so I see the way Docker history on this Paketo one, this is 5.6f. I can also see that this one would automatically split the application into libraries, dependencies, application files, and so on. So again, you wouldn't have to take care of this step. All right, if you happen to use Spring Boot, then you can use this also as a plugin in Maven and Gradle that would basically pull in this mechanism and build your image with that. Either way, the pack command works as well, and so does it the same for like other languages, like frameworks like Micronaut or Quarkus. So it shows me 0 minutes, so I probably should come to an end. Just one more quick advertisement. I'm going to give another talk tomorrow with my friend and speaker colleague Tiffany. This is going to be about observability of applications in general in the area of Kubernetes. So it's going to be a 3-hour deep dive session. Would be nice if you come around. And this is again the link for the repo. And with that, I would say thanks very much for listening and wish you all a nice evening.